Okay, we're going to do problem 219, converting position graphs to velocity graphs. We'll also calculate displacements and average velocities for the whole motions. So we'll start with displacement. Looks like we end this one at 1 meter. We began at 4. So delta x is xf minus xi. That'll be 1 meter minus 4 meters, so negative 3 meters. Average velocity is delta x over delta t. It's also the slope from the beginning to the end, if you look at it graphically. So it's negative 3 meters in 10 seconds, which would be negative 0.3 meters per second. Over here we begin at 2 meters, we end at 4 meters, so our delta x is 2 meters, and our average velocity 2 meters in 10 seconds would be 0.2 meters per second. Again, it's the slope of that line from the beginning to the end. Okay, let's calculate the velocity during each segment so we can draw the velocity graph. So we're looking for the slopes here. The slope here is 0, so that's easy enough. Slope at the end, also 0. Okay, in this section, the delta x, we go from 4 to 3. So the delta x is negative 1 meter. The v is delta x over delta t, or the slope of that line, same thing. And that's negative 1 meter over 4 seconds, so negative 0.25 meters per second. Here the delta x is also 1 meter. Negative 1 meter, rather. Oh, sorry, it's 3 to 1, so it's negative 2 meters. And that happened in 3 seconds, so our v is negative 2/3 meters per second. So this corresponds to these next 4 seconds, so we're going to look for negative 0.25 and then negative 2/3 for the next 3. Okay, so we don't have any direction changes there. We're going in the, the backwards direction, the negative direction, whatever that direction is the whole time. Either that or stopped, but we're not turning around. Okay, in the next one we only have 2 slopes to calculate. So in this first section we have a delta x. We go from 2 to 6, so we have a delta x of 4 meters. The delta t is 6 seconds, so that'll be 2/3 meters per second. In this next one, the delta x is negative 2 meters, because we go from 6 meters to 4 meters. And the v is then negative 1/2 meter per second, because that takes place in 4 seconds. Alright, so we go from 2/3 meter per second for the first 6 seconds to negative 1/2. And there is a direction change there because our velocity changed sign. So the velocity graph went across the axis. The position graph had a corner in it. There had a bend. Went from up to down. Okay, so again, just calculating the slope for each section. As long as the slope is constant, so is the velocity. So that's why we have so many flat velocity graphs here, because these slopes aren't changing.